Hello everyone, welcome to the web learning series. In this presentation, we are going to see the counter with unused states. The circuit with n flip-flop has 2 power n states, but it is not necessary that the sequential circuit should use all the states. We can design the circuit skipping few states. These states are called unused states. However, once a circuit is designed, outside noise may cause the circuit may enter into unused state. In that case, it is necessary to bring the circuit back into original sequence of state during the next clock pulse. Otherwise, that circuit becomes useless. Now, we shall design a 3-bit counter with some unused state. In this example, we shall design a 3-bit counter skipping two values 0, 1, 1 and 1, 1, 1. However, due to some noise or interference, the counter may go to the states called 0, 1, 1, that is decimal 3. We should ensure that the circuit goes to 1, 0, 0 after the application of next clock pulse. Similarly, even though 1, 1, 1 state is not present in the sequence, our design brings the circuit back to the next stage, that is 0, 0, 0 after the next clock cycle. Our first process in the design is to construct the state table, which consists of the present state, next state, and the flip-flop inputs. In this example, we can see the present state and the next state. For 0, 0, 0, the next state is 0, 0, 1. For 0, 0, 1, the next state is 0, 1, 0, and so on. The next step is to find the input of 3 JK flip-flop. Using excitation table, we can find all the flip-flop inputs. Here you can see for the present as well as the next state value of 0, 0, the flip-flop inputs are 0 and X as given in the excitation table. In the same way, the values of 1, X for 0 and 1 states are also found, and X, 0 for 1 and 1 state. Now repeat the same process for the second JK flip-flop JB and KB as given in the presentation. Finally, complete the table with third JK flip-flop JC and KC. After completing the state table, obtain the Boolean equations for each and every flip-flop inputs with the help of Karnaugh map. Now we shall analyze the circuit to determine their effects. In this presentation, we can see the counter goes to the normal sequence, that is from 0, 0, 0 to 0, 0, 1. Here you can see the present state is 1, 1, 1, which is an error actually because the sequence 1, 1, 1 is not available in our design. Now let's see how the circuit brings back to the normal sequence 0, 0, 0. B output is given to the input of first JK flip-flop. So the output of this flip-flop becomes toggle and its states becomes 1 to 0. Second flip-flop J input gets the value from C and K input is connected with logic 1. Now this output is complemented, that is 1 to 0. And third flip-flop's J input gets the value from B bar, which is 0. So the output of this flip-flop is always 0. From this, it is clear that the counter returned to the normal sequence 0, 0, 0 from 1, 1, 1 in the next clock pulse. In this way, we shall ensure the circuit get back to its normal sequence. Thus, in the counter circuit, if it happens to be in one of the unused state, it eventually reaches the normal count sequence after one or more clock pulses.